Hey everyone, so in this video we're going to go ahead and introduce a lot of the main nomenclature that we're going to talk about when we have hypothesis testing. So this is going to be very kind of definition and little example heavy without doing a lot of math until kind of the end of this video. So closer to the end we'll kind of see what the math part is like, but what we'll be doing first is kind of talking about all of the nuts and bolts that are associated with hypothesis testing. All right, so if we're familiar with the scientific method, it's going to be remember it's a procedure that we have for formulating hypotheses from observations, testing, and modifying those hypotheses to add knowledge to theories about the natural world. So the scientific method is to start by making an observation, then to form two hypotheses, some null hypothesis and an alternative hypothesis from this observation. Experimentally test the alternative hypothesis, and if the results support the alternative, then we're going to reject the null hypothesis, and if the results do not support the alternative hypothesis, then we'll fail to reject the null hypothesis. And so then we will kind of keep retesting this over and over again, starting back from step 2, maybe with some new hypotheses based on whatever the results are. So here's how we're going to go ahead and use the scientific method in statistics. So in statistics, a hypothesis is a statement about a population parameter So remember, these are things like mu, p, sigma, or sigma squared, and the observation is made by calculating sample statistics from the population. So our hypothesis testing is going to involve making some sort of conclusion about a population using information from the sample. Now the scientific method is going to require us to have two hypotheses. One of these is going to be our null hypothesis. We're going to denote this as H naught, and it's what our assumption is. Our assumption, or otherwise commonly accepted fact. Put fact here in quotation marks. So this could be something along the lines of, say, if I had a six-sided die, it's commonly accepted that when you roll a six-sided die, you have a 1 out of 6 chance of getting any of the particular sides. But of course, the assumption there is that it's evenly weighted. And so we had the worksheet 7 where we talked about rolling a 20-sided die and trying to determine whether or not it seemed like that was evenly weighted based on the rolls we had made. And so we were kind of looking at, kind of thinking about whether or not that was something that would be evenly weighted, or if it seemed like it was weighted strangely. So our statement about the null hypothesis will always contain the population, the parameter, and some form of equality. So here, if the original claim includes an equality, so something like less than or equal to, greater than or equal to, or just equals to, it is the null hypothesis. Otherwise, if it doesn't include the equals, so less than, greater than, or not equal to, it is the complement of that original claim. And so we could maybe even use it as our null hypothesis. So, or sorry, not our null hypothesis, our alternative hypothesis. So our alternative hypothesis is the claim we're making. In other words, it's what we are trying to prove. And so this is always going to contain the population parameter and either a less than or equal, or a less than, or greater than, or a not equals to. This is our statement that is true if the null hypothesis is false. Okay, so in a hypothesis test, what we're going to do is we're going to assume the null hypothesis is true in order for us to test if the alternative hypothesis is statistically likely to happen. And how we do this is we calculate the probability of getting our sample statistic that we end up getting, or something even more convincing against the null hypothesis. So if this probability is large, in other words, our sample is likely to happen, assuming the null hypothesis, then our assumption's probably right, and we will fail to reject the null hypothesis. However, if we have a small enough probability, and we'll talk a little bit about what a small enough probability means, it means our sample is unlikely to happen, assuming the null hypothesis, and so that means that we're kind of making our null hypothesis, that assumption we make is probably wrong, and so therefore we would reject the null hypothesis. So when we're looking at forming our conclusions from our hypotheses, we're going to have one of two different results. Either we're going to fail to reject the null hypothesis, H naught, which means there's not enough evidence to support the alternative, so support H1, or we will reject the null hypothesis, in which case there is enough evidence to support H1. So remember, we talked about this a little bit in the last video, but we're never going to accept the null hypothesis. So just because we didn't find enough information to reject the null hypothesis doesn't mean that the null hypothesis is true per se. It just means that our sample that we had didn't give us enough information to suggest that. So to prove that a hypothesis is true or false with absolute certainty, we would need to know all the knowledge about the entire population, which isn't really likely to happen in the real world. It's 2020 right now, so a lot of you have seen, or your parents have seen, the census come in the mail. So that's a way to try to get information about the entire population. But that's something that's very resource intensive, and so is not something that happens all that frequently. Usually we only have information about a population if the information about a sample that came from the population. Or sorry, let me rephrase that. Or say that again, because I stumbled over it. Usually the only information we have about a population is the information about a sample that comes from the population. So the process of hypothesis testing is going to give us some way of using the sample to try to make some educated guess about whether or not the thing we're assuming about the entire population is likely to be true, or the claim we're making about the population is likely to be true. So we're going to go through a couple of examples of looking at some statements and determining how to translate that into kind of null and alternative hypotheses, and then talking about what we would phrase our results as. So let's test the claim of the standard deviation of adult IQ scores is greater than 10. So a couple of things that we want to note here. We're talking about standard deviation. So in our null and alternative hypotheses, we're going to be looking at the standard deviation. And so if we're trying to look at this claim, the claim is that the standard deviation is greater than 10. Now remember, when we're looking at these claims, if we don't have the or equals to, this is going to be our alternative. So here, the alternative is that the standard deviation is greater than 10. And so the complement to that is that the standard deviation is less than or equal to 10. So our null hypothesis, our assumption that we're going to start here with, is that the standard deviation is less than or equal to 10. And we need to see enough evidence from the sample to lead us to believe that the standard deviation for the population is greater than 10. So note that even though we get a sample that has a standard deviation greater than 10, that doesn't necessarily mean that we can assume that is true for the whole population. We're going to see how likely it is that we get something a little more than 10, given this first assumption. All right, so a hypothesis test on this claim ends up resulting in failing to reject the null hypothesis. In non-technical terms, what this means is that there is not enough evidence to support that the standard deviation of adult IQ scores is greater than 10. Okay, let's look at another example. So let's say we've got an M&M package label includes some sort of claim about the proportion of green M&Ms being at least 0.2 or 20%. We want to test this claim. So here we're looking at a proportion. And so when we're looking at proportion, remember the thing that we're using is P. So our population parameter is P. And so our claim is that P is greater than or equal to 0.2. So remember, when we have this or equals to, that means we're talking about the null hypothesis. So here P is greater than or equal to 0.2, and our alternative is going to be that P is less than 0.2, so the complement of that. So if we look at this hypothesis and these claims, a hypothesis test ends up resulting in rejecting the null hypothesis. So what that means in non-technical terms is that there is enough evidence to support that the proportion of green M&Ms is less than 0.2. So if we're rejecting the null hypothesis, then we have enough evidence. If we're not rejecting the null hypothesis, or we fail to reject, then we don't have enough evidence. So those are kind of our two worlds that we live in. All right, let's look at one more. Let's go ahead and test the claim, or talk about trying to test the claim, that the average age, underline average, of the audience at a jazz concert is 50 years old. So here we're talking about the average, so the average is going to be denoted by mu, and so our claim is that mu equals 50, so that it is 50. And so since it's an equals, we make that our null hypothesis, and so the alternative is the opposite, so it's non-equal to 50. When we look at our hypothesis test, if at the end of the day it fails to reject the null hypothesis, then that's us saying that we do not have enough evidence, or there is not enough evidence to support that the average age of the audience is 50. I don't know about you, but I'm glad about that. Jazz is pretty cool. I'm a fan of jazz. I'm not 50, so I could see some younger crowd being there, or maybe the claim is that it's actually greater. But right, we just said not equals to, so I'm not 50. I'm pretty happy about that. Pretty pumped about that result. All right, so let's talk a little bit about the error we could have. So note that we're using a sample here, and we don't have information about the entire population. So it's possible for us to get some sort of bad sample that results in, us drawing the wrong conclusion. So since we don't know about the population, and the result of a hypothesis test is whether or not the alternative is likely to occur, there's a chance we could be wrong. So there are two types of errors. Type 1 and type 2. So type 1 error is the idea of rejecting the null hypothesis when it is actually true and type 2 is failing to reject the null hypothesis when it is false. All right, it's going to be a little bit tricky to understand. So let's, who here has ever heard the tale of the Big Bad Wolf? Okay, you can stop raising your hands. This is a video. So, in the story of the Big Bad Wolf, or not the Big Bad Wolf, the Boy Who Cried Wolf, we kind of had two ideas. There was one idea that there is no wolf, and then there's the alternative idea that there is a wolf. All right, so we've got this boy who's crying wolf, and how the story goes is that the boy is tending a herd of sheep, and to kind of play a prank on some of the other villagers, and so he runs into town, and he yells, "Oh no, there's a wolf! There's a wolf!" And so what happens is everyone believes him. They kind of grab their pitchforks. They come running to the fields to try to defend the sheep from this wolf. And it turns out that there actually is no wolf. So the villagers kind of fall for a type 1 error. They reject the idea that there's no wolf when actually there was no wolf. So then the boy does this again. A couple of days later, he comes and he yells, there's a wolf, thinking, oh, I can get him again. So the villagers grab all their pitchforks. They come running to help the boy. And it turns out there's no wolf again. So again, they make this type 1 error. So they rejected the idea that there's no wolf when it turns out there actually was a wolf. They reject the idea that there's no wolf, and it turns out there really was no wolf. Now a couple of days later, the boy actually sees a wolf. And so now there is a wolf in the fields. And so the boy yells to all the village people, oh no, there's a wolf. But nobody believes the boy. And so now there actually is a wolf, which means the null hypothesis of there not being a wolf is false. And so now we're creating a type 2 error. So we're failing to reject the null hypothesis, which they now believe, even though it actually is false. It actually is the case that there is a wolf. And so the boy goes back to the fields to try to defend the sheep from the wolf, and the wolf eats him. So the moral of that story is supposed to be, not to tell a fib about something so important, because then nobody will believe you when it actually comes time. But for us, it's nice because we get to talk about type 1 and type 2 errors. So type 1 error is the idea of crying wolf, of saying that we have a wolf even though there is none. And a type 2 is thinking, you know what, I'm pretty sure there's actually no wolf there, when the truth of the matter is there is. So just kind of a example to think about that. All right, let's keep going on and talking about some of this terminology. We're almost halfway through. I know it's a long video. All right, so we've talked a little bit about significance level before, this alpha. And so the significance level is the probability of making a type 1 error. And so the idea here is that if we set our, we talked a little bit earlier about the idea that if we wanted to go ahead and reject the null hypothesis, we needed a probability that was small enough. And so what we're going to do is we're going to use this significance level, this alpha, to determine what that likelihood is that we say it's less than that. Well, it's a little too unlikely for me to believe now. So there are a few different values we could have here based on how serious it is to make this mistake. And so remember, the type 1 error is the idea of rejecting the null hypothesis when it's actually true. So typically the choices we might make for alpha are 0.01, 0.05, or 0.1. So after we've calculated our probability of getting our sample data we have, assuming the null hypothesis is true, we're going to compare the probability that we get to the significance level. This is going to be kind of what is defined as a p-value, which we'll get to in a second. And this is how we determine whether or not the probability is considered large or small, and whether or not we fail to reject our null hypothesis. So the p-value is the probability of getting our sample data or something more convincing assuming the null hypothesis is true. So since we have to make this assumption about whether or not the probability or our null hypothesis is true, since we have to make that assumption, this is actually a conditional probability. That we are going ahead and calculating. So remember that since when we're trying to do our hypothesis testing, we're trying to make a conclusion about a population using our information from a sample. So to prove something about a population mean, we're going to have to use our sample mean as a guide. So we use the sampling distribution of x bar. If we want to prove something about the population standard deviation, the variance, we can use the the sample standard deviation or variance as a guide. So to predict something about sigma, we'll use S. So we use S's sampling distribution. And if we want to prove something about the population proportion, we have to use our sample proportion as a guide. So we'll use p hat's sampling distribution. So when we're going ahead and kind of determining these things, what we're going to want to do is we're going to have some sort of statistics we can use in order to figure out what that probability is, what our likelihoods are. And so each hypothesis test is going to involve us obtaining a test statistic. And so just to create a little summary of all of these seen before, we're going to kind of denote the test statistic as t. And so if we're talking about a population mean, t could be x bar minus mu over sigma over the square root of n. As remember, we're using the sampling distribution. So with the sampling distribution, our standard error is the thing that we're using here. And so remember that this is going to be our z-scores that we've talked about. But that's only if we know the population standard deviation. If we don't, we could instead use x bar minus mu over the sample standard deviation over the square root of n. Again, we need to use this standard error because we're using the sampling distribution. But then remember, this is going to be approximated by our t distribution for degrees of freedom of n minus 1. So we kind of have two different things we might use, t or z, if we're trying to create a statistic for the population mean, and it's going to depend on whether or not we know the population standard deviation or not. When we look at creating a test statistic for p, p hat minus p over the square root of p times 1 minus p over n. And so again, remember, this is what we get for our sampling distribution's standard error. And so this, when we're talking about the population, we get to use, or the population proportion, we get to use z. And last but not least, if we ever wanted to go ahead and create a test statistic for our standard deviation or our variance, what we might do is n minus 1 times s squared over sigma squared, which is going to be our chi-squared with degrees of freedom n minus 1. Again, this one's not going to come up in this class very often, but I felt it was important to at least show it. Alright, so we also can have the idea of a certain number of tails for our test. So we can have something that's either left-tailed, right-tailed, or two-tailed. So we have to kind of determine what our tailing is at the beginning, and so this will help us determine what more convincing data would mean every time we talk about our alternative hypothesis. So we need to know exactly what we need to see these values be from our sample to convince us that H1 is true. And so we determine how our test statistic will change if we get more convincing data for these different things. So we have first the idea of a left tail test. So the left tail test means that smaller values of our test statistic are more convincing that the alternative hypothesis is true. So here, say I've got something like this. A left tail test means that I only care about small values from our sample. Small values are the thing that will cause us to reject in some way, shape, or form. So this is when we have things like mu is less than some value, or our population proportion is less than some value, or sigma is less than some value. So these are different potential alternative hypotheses where you're going to see some sort of left tail thing come out as the thing we're looking at. We also have right-tailed tests, which, as I'm sure you'd expect, means that larger values of the test statistic are going to be more convincing that the alternative hypothesis is true. So here, again, we can look at a distribution. For a right tail test, what we're going to care about is kind of things on the right-hand side. And so these are going to convince us anything kind of over in this region that we get for our test statistic will convince us that the alternative hypothesis is true. And so this would kind of denote alternative hypotheses of maybe mu being greater than some number, or p being greater than some number, or our standard deviation being greater than some number. And then last but not least are the idea of two-tailed tests, and this means that larger or smaller values of the test statistic are more convincing that the alternative hypothesis is true. So now we don't just care about whether or not we are above or below. We care about, both sides. And so we're going to see a two-tailed test when we're looking at the idea that whatever our population parameter is not equal to some number as our alternative hypothesis. All right, so let's get a little bit of practice on whether or not we end up having something that is left tail or right tail or two-tailed. So here, let's take a look at this first one. If we're saying H naught is greater than 45, where n is greater than 30 and the standard deviation is known, let's talk about the test statistic we would use and what type of tail it is. So because we have greater than, this signifies that it is a right tail test. So if we have kind of larger and larger X bars, we'll be looking at more convincing data. And so, again, to kind of signify this, do something along the lines of this. And if we wanted to know what our test statistic was, well, we're talking about a population mean here. So we need to use some sort of x bar minus mu. And so the next question will be, do we know our standard deviation for our population? And it says we do. So we would use the standard deviation over the square root of n. And so this would mean that we would use a z-score to make our determination. We'll talk about how we use this z-score to make the determination soon and in the next video as well, but just some things to look at. All right, so let's say that we wanted to go ahead and look at the same alternative hypothesis, but now we don't know the population standard deviation. So again, this tells us we have a right tail test. But now when we're trying to create our test statistic, again, we're talking about the population mean. So since talking about the population mean, we have x bar minus mu, but now we only know the sample standard deviation. And so now we're looking at t sub n minus 1. And so now we need to use the student's t distribution in order to calculate what our statistics were. All right, now let's say we wanted to go ahead and create something involving the population standard deviation being less than 125 for our alternative, and we're going to the original population is normal. So note that this less than means that we are left-tailed. So as we look at the distribution, remember chi-squared looks a little different than other distributions. We'll be looking at having smaller values of our sample standard deviation being the thing that helps us reject the alternative hypothesis. And so here, our test statistic would be n minus 1 over s, or times s squared over sigma squared, which will be chi-squared of n minus 1. And so this would be our test statistic we would use. And last but not least, for these examples, if we wanted to go ahead and look at our population proportion being not equal to 0.72, where we have enough information in both categories in order to be able to do our statistics. We want to know what type of tailing this will be and what type of statistic we should use for our test statistic. So this not equals to tells us we have a two-tailed test. And so as we take a look at a distribution for that, anything that is a small enough value from our sample proportion or a large enough value will cause us to reject the null hypothesis. And so when we are creating our test statistic, we'll have p hat minus p over the square root of p times 1 minus p over n, which is a z-score. Now I want to kind of point out something that I may have glossed over throughout all of these. When we're looking at all of these different test statistics, when we say that we're looking at mu, or we're looking at the population standard deviation, or the population proportion in each of these, we're going to be using the value that we're assuming for our null hypothesis. So here, if we looked at this example, because we're assuming mu is greater than 45, that means our H naught is that mu is less than or equal to 45. And so here the value to be put in for mu would be 45. Similar for this one, H naught is that mu is less than or equal to 45. And so we will replace mu with 45. Here, if we're looking at the idea that the standard deviation is less than 125 for our, I want to point out these red lines are not underlines. I'm just trying to show and denote that this is the symbol that tells us which tail we have. Here, H naught will be that the standard deviation is greater than or equal to 125. And so this value for sigma down here will be 125. And last but not least, if we're assuming that H naught is a P is not equal to 0.72, the null hypothesis is that it is equal to 0.72. And so here, every time we see this P, it'll be 0.72. And so that means that in all of these, it mostly requires us to know whatever n is and also what our, in this case, our population standard deviation, sample standard deviation, but our sample statistic that we're using to test is the thing we're going to be focused on. All right, so there are two main ways of going ahead and performing a hypothesis test. We're going to look at one of them in this video, and the next we'll focus on the other one. And then we'll kind of have a worksheet that you guys can play around with in order to try these things out on your own. All right, so let's say we want to perform a hypothesis test with the critical value method. So this is going to be one of our two ways of performing this hypothesis test. We are going to, in order to do the critical value method, what we're going to do is we're going to compare our test statistic that we get to some critical value. If the test statistic is more extreme in the direction of the alternative than the critical value, then we're going to reject the null hypothesis in favor of the alternative hypothesis. If the test statistic is less extreme than the critical value, we do not reject the null hypothesis. So let's walk through a whole example as opposed to kind of these little partial examples we've seen so far. The American Automobile Association reported that the mean price of a gallon of regular grade gasoline in the city of Los Angeles in 2017 was $2.82. A recently taken simple random sample of 50 gas stations in Los Angeles had an average price of $2.77 for a gallon of regular grade gasoline. Assume that the standard deviation of prices is 0.15 or 15 cents. An economist is interested in determining whether the mean price for all Los Angeles gas stations is less than $2.82, as was stated in 2017. We want to use the critical value method to perform a hypothesis test at the alpha equals 0.05 significance level. So here, we need to first know what our claim is. So we're told that put some paper under this so I don't keep punching holes in this. We are told that the economist wants to know if the mean price is less than $2.82. And so that means, since we don't have an equality in that this is the thing we're testing. This is our claim. This is our H0 or H1. So H1 is that mu is less than $2.82, and H0, our null, is the complement of that. so that it's greater than or equal to $2.82. So here, some things we want to check. We are told that we have a sample of 50 gas stations. We had an average price of $2.77, and we're going to assume the standard deviation is 15 cents. So here, N is 50, X bar is 2.77, and because we're making an assumption on the standard deviation as opposed to looking at our sample, it's going to be our population standard deviation, and so we have a standard deviation of 0.15. So since n is greater than 30, our sampling distribution for our sample mean is going to be approximately normal. So remember, this is one of the assumptions that we have to make in order to use this. And so when we look at our test statistic, we're going to be looking at having x bar minus mu divided by the population standard deviation over the square root of n. And so here this will be 2.77 minus, because we're using 2.82 as our value, we will subtract 2.82 and then divide by 0.15 over the square root of 50. And when we do all of this, we can put this off to the side, we get approximately negative 2.36 as our z-score that we're looking at. So because our alternative hypothesis is telling us that we're looking at things that are less than 2.82, we have a left tail test. So what we're going to be doing is we're going to be looking at our z-scores here. We have a value of 0. And so what we want to do is we want to figure out what our cutoff is for being extreme based on our alpha. So we said that alpha equals 0.05. So if we have anything that would suggest that we had a probability less than 0.05 based on, say, our z-score, then we'd want to go ahead and be able to determine that. So using the critical value method, what we're going to do is we're going to have our cutoff, z. So z. So this is a z that we got for the test statistic. Whereas this is the z for our critical value. And so here, if we want to know what this is going to be, we'll take the inverse norm of 0.05, 0, and 1, and we'll get negative 1.645 as a result, approximately. So the idea is that when we take a look at negative 1.645, once we get to this point, there's only 5% of the area under the curve to the left of that value. And so if we ended up having a value that was more extreme than that, what that means is that as we kind of move further this way, there's less and less of the area under the curve than 0.05 or 5%. And so note that our test statistic was negative 2.36. And so since our test statistic was more extreme than our critical value, in other words, since negative 2.36 was less than negative 1.645, we reject the null hypothesis H naught. So this is our conclusion. So in kind of layman's terms, should have spaced this out a little better. There is enough evidence to support that the mean price for all LA gas stations is less than 2.82. So this is our critical method. We're going to go ahead and start with our null and alternative hypotheses based on our claim. We'll create our own test statistic, and we will determine what our value is for determining whether or not we should reject. And if we are past that in the direction that we have, since we're looking at a left tail test this time, we're looking at things, to the left of that, then we will reject our null hypothesis. If we had had a right tail test, we would have said if we were to the right of whatever value we had found, then we would reject the null hypothesis. And if we had a two-tail test, we would have had values on both sides, and if we were past either of those, then we would have rejected our null hypothesis. We'll kind of see some more examples of this as we go through the next video, when we look at the p-value method, and as we go through the worksheet.